Okay, so let's pick up where we left off. Last time we said that if your rate law is a simple case where the rate of consumption of a reactant, let's say R, is either first, zero, or second order with respect to R, okay? So I'm going to put little r here as the order of reaction with respect to R. Then integration of this differential equation will give you what you call the rate laws, which will allow you to easily distinguish between zero order, first order, and second order. What did we say the plot of R would look like versus time if it's zero order? Straight line with what slope? Negative slope, right? And the slope of that is negative k, right? And if it's first order, then what you need, you should be able to show that natural log of R versus time would be a straight line again with a slope equal to negative k. And if it's second order, then what you'll need to do is, so if you've tested whether it's zero or first order and you find that it's not zero order, it's not first order, you can check if it's second order by plotting the reciprocal of R versus time, and you should get a straight line, okay, with a positive slope, and that slope is equal to k, right? Now, and like I said, typical lab scenario, you would be measuring something that is proportional to the concentration of R. And you really don't need to calculate R based on that measurement because, as you can see, if X, some property X is directly proportional to R, so it's a constant times concentration of R. If you substitute, okay, you can say that R is equal to X over C. If you substitute X over C for R in these expressions, what do you find? You'll still find that in the case of a zero order reaction, okay, X would, in this case, would turn out to be negative CKT time plus X naught. So you still get a straight line. So if you plot X versus time instead, you're still going to get a straight line with a slope of negative K. Similarly, if you plot ln of X versus time, provided your constant is positive, okay, then you also get a straight line with the slope of negative K. So just in case your constant is negative, then you just take the absolute value of X. You don't want a negative. You can't take the logarithm of a negative number. Okay? And same idea. In this case, your slope is going to be negative K. I'm sorry. In the case of zero order, the slope is going to be equal to negative C times K this time. Okay? And in the case of zero, the first order, the nice thing about the first order one is the slope is still going to be equal to negative K. However, if you have second order, your slope will now be equal to K over C. Okay? Provide if some property X is equal to a constant times the concentration of R. But still, the graphs will allow you to determine whether it's zero order, first order, or second order. It's only the first order plot that would give you the rate constant right away. The zero order and the first order and the second order, you kind of have to know what that proportionality constant is. Okay? So, what if X, the property you're measuring, is not directly proportional to the concentration of R, but it's linearly related? That means X is equal to some constant times concentration of R plus another constant. Okay? Then you'll find that if it's zero order, a plot of X versus time is still going to be a straight line. Why is that? If you substitute R is equal to X over C, what do you get? You say R equals negative KT plus R naught. And so that's X over C is negative k, I'm sorry, x minus d over c this time, right? So you're going to say then that x minus d over c is equal to negative kt plus r naught, which would be x naught minus d over c. So what happens there? Multiply both sides by c, what do you get? X minus d equals negative k ckt, right? Plus x naught minus d. And your d, negative minus d cancels from both sides. You get the same equation. Okay? So all it does is it shifts your graph upward or down vertically. Okay? Depending on what d is. Your x versus time. Okay? So you still have the same slope. It's going to be negative ck. Now, what if you have a first order rate law? Then, in this case, okay, let's put ln r equals negative kt plus ln of r naught. Let's make the substitution. You can see that ln of x minus d over c equals negative kt plus ln of x naught minus d over c, right? And what do you get here? It's going to be ln of x minus d minus ln of c equals negative kt plus ln of x naught minus d minus ln of c, right? So ln of c cancels out. And so you can plot of ln of x minus d versus time, you still get the same slope. It's going to be equal to negative k. And again, you have to take into consideration the fact that x minus d might be negative. So what you do is just take the absolute value. Okay. Now, what is d? I think we talked about this last time. Huh? D is in fact the value of x at infinite time. Why is that? Because if you look at your expression, okay, what did we say x was? It's a constant times r, right? Plus d, right? What happens as t approaches infinity? What happens to your r? Approaches 0, right? And so what happens is your x is going to approach the value of d. So what do we do then to get determine the value of d? You wait until infinite time and make your measurement for x, right? And so how do you wait an infinite amount of time? You can't, but for reactions that are sufficiently fast, what you would do is you would wait one day or 1 week later, you make your final measurement. Okay? So if your data looks something like this, x versus time, okay, let's see, x versus time, where's x, what's your d right there? You can see it's leveled off here, it's already at equilibrium here, right? So that's your x at infinite time, so that's your d. Okay? So you run your reaction now, wait a week later to make your final measurement, you get your x of d. Okay? So it's still useful, but that it has, you kind of have to wait until that reaction actually reaches equilibrium for you to be able to analyze your data. So what if you can't wait? There's another method called the method of Guggenheim. I don't know if I have that on this slide. In the method of Guggenheim, you do what's called a time lag. X at time t, okay, minus x at time t plus d. All right, and in this case, what will happen? It's going to be CR minus at time t minus R at time t plus d, right? What happens to your d? I'm going to call it a different letter, delta, t plus delta. Delta is your time lag, okay? So what would happen? Okay, let me fix this up. This is going to be CR plus D at time t, right? Minus C times R at time t plus delta minus D. You'll notice that your D cancels out. So this just gives you C times R at time t minus R at time t plus delta. Okay? And if you plot that versus time, ln of x, absolute value of xt minus x of t plus delta versus time, you're going to get a straight line. So this is called the Guggenheim method. And you can prove this, and we'll do that some other time. Okay. So what I want to do now is just show you the experiment that you're going to be doing in the lab. First part, that would be just determining whether your rate law is zero order, first order, or second order. Okay. So let's take a look at our experiment. What we'll be doing is you are going to be studying the fading of phenolphthalein and sodium hydroxide. Okay? So for our experiment, you're going to be looking at phenolphthalein, the same phenolphthalein that you use in your acid-base titration, plus sodium hydroxide. Okay, this will give you, okay, phenolphthalein is an acid, okay, and it will give you a negatively charged ion, an ion with a -2 charge, okay, and this ion is going to be responsible for the pink color of your phenolphthalein in solution, okay, and this is going to fade, and we're going to determine the rate law in terms, so this is going to be a very fast reaction. It's converted right away to a pink ion, an ion with that's responsible for the pink color. That's a very fast reaction. What we're going to be monitoring in this experiment is the fading of this pink color, so the conversion of this negative ion into something else. Okay, in your handout you'll have the details of this reaction. So we need to determine the order of the reaction with respect to the concentration of the pink ion. Okay? And so, let's do that. I have here some sodium hydroxide. Okay? And I'm going to put phenolphthalein in it. And you can see for yourself that the color fades over time. Oh! Okay, so here it is. Phenolphthalein, sodium hydroxide. You can watch that fade, and I'll put another one here in the spectrometer, and we'll monitor the concentration So I'm going to put some more sodium hydroxide in another cuvette. Here. Let me calibrate this cuvette first. So what we're going to have, okay. First thing is I need to calibrate. So calibrate my spectrometer. It's warming up. It's going to be a while. 90 seconds to warm up. You notice the phenolphthalein fading? Slightly. And by the time this is done warming up, it will be fading. It will have faded. Pause the recording here. Okay. So warm up complete, finished. I have a blank in my cuvette. So when you're calibrating, you put your blank solution in your cuvette, in your spectrometer, and then finish calibration. Okay. All right. All right. So let's put the sodium hydroxide with the phenolphthalein in your cuvette. Okay. And start collecting data. So here it is. And I'm going to collect the absorbance and let's see what happens. And there is your spectrum. Okay. Now, typically, if your absorbance is over 1, you can't rely on it too much, right? And when you want to monitor concentration versus absorbance, you want to monitor the absorbance at the wavelength where you have the strongest absorptivity, right? So strongest absorption. So let's wait for that to reach 1. Let me change the y-axis option right here for now. So I'm just going to get it from 0 to 1. And change that scale from 0 to 1. And let's wait for that to hit. Let's change that to 1.1. Hit 1.1. And let's wait for that to hit 1. And let me show the grid on this one too. Graph options. I want grids. How do I do grids?
At the bottom of the graph options, it says grid.
Where does it say?
Like it's that little box. Matrix style, that's all on the grid.
Oh, okay. Minor. Okay. Let's time it from the time it. Okay. Now, for now, let's just determine what that wavelength we should be using for our to monitor this reaction. So, where is that peak wavelength happening? Approximately where? Right around there, right? So that's around what? This is 500. This is 600. 520, 540. I see 520, 540, 560. So between 540 and 560. Okay. Where's our peak value here? Right around 552, 553. Okay, so we're going to do another run. This time we're going to monitor how long it's going to take. We're going to monitor the absorbance versus time at 552 or 553 nanometers. Okay, so I'm going to set my next data collection. So let me just stop that data collection right there. You can see your color is still fading. By the way, how do you explain, how do you correlate that with the color of your phenolphthalein? Remember, our phenolphthalein is pink, right? So it's sort of red. Remember your color wheel. So Roy G. Biff. What's the complement of red? Green. And where is the maximum absorption happening? The strongest color that's being absorbed by your the ion responsible for the color of phenolphthalein in base is green. Okay, so that's why what you see is pink. Strongly absorbs green. All right. So what was that again? 520, 553. 553. So over here, okay, when you go to the lab, when you do this experiment, go configure a spectrometer. You can select 553 as the wavelength where you're going to monitor your, so 552.9 is where you're going to monitor your absorbance. So when you're doing your kinetics experiment, you got to be monitoring absorbance versus time, okay? So make sure you check this box right here. My pen doesn't work. Okay, so absorbance versus time right here, and then you specify the absorbance that you're going to be monitoring. So around 553, that's where the peak of your absorption is. Okay, so I'm going to click OK on that one. I'm not going to store this latest run, so I'm just going to say no. And now what's happening? It's actually monitoring the absorbance at 552.9, okay? So we're going to do this again. This time we're going to collect data. Absorbance versus time. How long should we be collecting? Let's set it up for just continuous data collection. So continuous data collection, okay? Just let it run, and we're going to collect a sample like every 5 seconds, 1 second. What's a good? Every second's too fast. Let's just say every 5 seconds for every sample. Okay, so we're going to collect data at every 5 seconds. All right, and I'm going to go ahead and make another mixture. Oh, look, it's all faded now. Oh, putting in the wrong thing. All right, this sodium hydroxide. Okay, I need somebody to hit the collect button the moment I added the phenolphthalein. As soon as I drop the phenolphthalein, click on the collect button. Okay, go. And And then I'm going to put this in. So you'll notice what's happening now. Okay, and that's our absorbance. Okay, I just put it in the cuvette, in the spectrometer. And it should be, so if we're monitoring absorbance versus time, this is what we'll be getting. Okay, now for any absorbance, it's like I said, anything above 1, we can just throw that data out in terms of reliability. We're going to rely more on the data we get after the absorbance drops down to 1. Okay. And let me change this scale so it will show the grid lines. All right, let's estimate the half-life of this. So I want you to set your timer. You got timers? Yeah. Turn it on when it hits 1, when the absorbance hits 1, okay? For how long? And we're going to time how long it takes for it to go from 1 to 0.5. That will be 1 half-life. Go. Okay, we're going to determine the half-life of this reaction. How long will it take before that absorbance reaches 0.5? Okay, I need someone to monitor how long it's going to take from 0.8 to 0.4. John?
It stopped. Oh, it's thinking every 5 seconds. So
There, 0.8, it just started. You got it? Okay. That's all right. We got the data anyway. We can collect it later. We can analyze it later. But from 1 to 0.5, it's still not there yet, right? Okay, I need somebody to start getting ready to start timing it from 0.5 to 0.25, the second half-life. Okay, so once it gets 0.5, gets to 0.5, I want somebody else to time it. How long is it going? From 0.5 to 0.25. There.
I started.
Okay. So how long did it take from 1 to 0.5?
A minute and 4 seconds.
Okay.
And I can do 8.25. Yeah.
So from here to 0.5, it took how long?
A minute 40.
Okay, so that's about how many seconds? 100 seconds? Ah, that's about right, from 100 to 200, right? So 100 seconds for our half-life. This is from absorbance of 1 to absorbance of 0.5. Let's see how long it takes to go from 0.5 to 0.25. Are we almost there? There.
A minute and 34.
A minute and 34. So that's about 94 seconds. from 0.5 to 0.25. So what would you say the half-life is? If it was zero order, what's going to happen to the half-life? It's going to get shorter, right? If it's second half-life, if it's zero order, would be half as long. Is that half as long? No. If it's second order, what happens? The half-life, after the first half-life, the second half-life is going to be twice as long. The second half-life twice as long. No. So what's the order of this reaction then? It's first order. 194 is more or less the same. Okay? Okay, so let's go ahead and stop this reaction. Stop this data collection. Okay. So I'm going to transfer this data to Excel. So we can do some analysis from there. Okay, so this is time in seconds, and this is your absorbance. And we're going to only analyze data after it's dropped to 1, absorbance of 1, right? So let me just hide these numbers. Hide. Okay. And what are we doing here? We're going to try to plot A versus time. Let's plot A versus time. Obviously, that wasn't linear, right? It's a curve. So let's try ln of A versus time. Ln of absorbance. So what would you have here? Equals ln of B22. So copy that down to the rest of your column. Control D to copy. And then what do? We graph. Insert chart, scatter plot. Don't connect the data points. This is not what I want. What should I do? Select data. Remove. Okay. Okay. Now I want to just plot one. X values would be time. So from 100 seconds to 365 seconds. And my ln of A would be my Y values. Okay. And we've got ourselves a straight line. Okay. And it's too crowded. Let's make our data points smaller. Marker style. How do I do marker style? Format? No? Layout? Format data series. Marker options. Let's make those smaller. Okay. Alright, so we've got a straight line. And our linear trend line would give you what? A negative slope. And so what's our slope? Negative 0.0072. So what's our rate constant? Let's do a regression on this one. That way we can get the right sig fig. So let's do a regression. How do you do regression? Data analysis, regression. Okay, Y values would be ln of A, right? And what would be our X values? Time. Okay. And I'm going to put my results over here below my chart. And hit OK. And so my slope is right here. Negative 0.007151 plus or minus 1.8 times 10 to the negative 5. So what would that be? 0.000018. So fifth decimal place. So 1, 2, 3, 4, 5 decimal places. Okay. And just so it's okay to keep an extra digit, because if we're going to be using it for something, some other calculation, so let's just keep an extra digit there. So how should I report this? Oops, what did I just do? Uh-oh. Okay. So it's here. The last sig fig is the 5, right? So if I put this in scientific notation, this is going to be negative 7.158 times 10 to the negative, okay, plus or minus 0.018, right? 0.018, oh, 0.019. 0.019. My last sig fig is that digit right there, times 10 to the negative 5. Oh, not negative 5. Negative 3. Okay. So it's 7.158 times 10 to the negative 3 per second is my rate constant. Okay. So if that's my rate constant, what is my half-life? I know this is first order, so half-life is how much? ln of 2 divided by k, right? First order. So what's ln of 2? 0.693 divided by k. What would that be? Oh, I've got Excel right here. I should be able to do it here, huh? So I'm going to say half-life equals ln of 2 divided by, what's my k? I can just use this number right here. The negative of this, right? Okay, so negative of F50. Okay. So it's 96.8. So 97 seconds. That's what we did. That's what we found, right? 100 seconds. And then the other one was not. The second half-life was 94. Okay. And so you can see that this one goes through at least, so it goes from 1, okay, to all the way to 0.15, right? You got a nice straight line, so you can be very confident here that this is a first order reaction. Okay, that's one thing you do need to realize about log. One thing you have to be aware of when you're doing log plots, typically they turn out linear, especially if you're looking at a small interval. So if you really want to be confident that your rate is first order, your rate law is first order, you have to go at least 2 or 3 half-lives. You should be able to show that it is, your log plot is linear over at least 2 or 3 half-lives. Okay, so that's how you determine your rate constant for first order process. Now let's examine the actual graph of just A versus time. So let me do another graph here. So let me just shrink this one. And let me just copy that output. But in this time, I'm going to change my data. This time I'm just going to plot A versus time, okay? Absorbance versus time. Okay. Oops. What did I do? Oh, I left the trend line there. Okay. So you can see it's not a straight line. So I'm just going to take out that trend line. Okay. So you can see, look, if you were to just did this experiment over, let's say, up to this time interval right here, if you just look at data from 100 to maybe 150 seconds, that might look like a straight line to you, right? This part right here, that looks like a straight line. So always keep that in mind when you're analyzing data. You can't just blindly say that log versus concentration versus time is linear in zero order. Okay, and even if it's second order, for example, if you put log versus time, if you're looking at small intervals, graphs tend to look linear. So you need to be able to look at a big enough range for time so you can actually determine whether it's first order, zero order, or second order. Right. Now, what was it I was trying to say? Let's look at the half-lives, okay? Let's plot the half-lives. Okay, from 1 to 0.5, how long did you say it took? 100 seconds, right? So yeah, here you go. From 100 to 200 seconds, that's one half-life. Let's look at the time it takes. So our half-life here, we say, is about 100 seconds. How long does it take to go from, let's say, 0.8, this is about 0.8 right here, right? It's about 0.8. How long? So that's 0.8 happens at 135 seconds. How long does it take to go from 0.8 to 0.4? Where is 0.4? Right here. Oops. That's 230 seconds. So 135 to 230, how long is that? So that's about 95 seconds. Okay. So you can see here that your half-life is more or less constant. And of course, the variation there has to do with what? Random errors, right? So you can see your half-life is constant. You don't have to go from, it doesn't matter where you start. Let's start from 0.7. What's our half-life if we start from 0.7? Okay. 0.7 is at 155 seconds. Okay. How long does it take for it to get to 0.35, right? Half of 0.7 is 0.35. Let's look at 0.35. Where is 0.35? Around here, okay? Around 245 seconds. So you're going from 155 to 245. It's about 90 seconds, okay? So you're getting a more or less constant half-life throughout this process. And of course, we're not getting the exact numbers here, right? So you can see there's some variability there. So that's what you need to determine. So now we've established that this reaction is first order. Okay? So what we're going to do in the lab is you're actually going to study the effect of the concentration of hydroxide on this reaction. Because what we've done here is we've flooded the reaction with sodium hydroxide. We have a very large excess of sodium hydroxide. So percentage-wise, the sodium hydroxide hasn't really changed very much. You have a very high concentration of sodium hydroxide, and your phenolphthalein concentration is very low. So what you'll do in the lab is you're going to study the effect of the concentration of sodium hydroxide, and you're going to study the effect of temperature on this reaction. Okay? And so that's what you'll be doing. Okay. Let me see. Let me just get rid of these. I mentioned earlier that you can do what's called the method of Guggenheim. Okay. And in the method of Guggenheim, you choose what's called a time lag. All right. And so give me a number. Pick a number. 75 seconds. Okay. Let's see. 75 seconds. Do we have enough data here? Okay. 75 seconds. So let's say my time lag is 75 seconds. So I'm going to use delta equals 75 seconds. What I'm going to do in the method of Guggenheim is I'm going to take absorbance at time t minus absorbance at time t plus delta. Okay? And then I'm going to take the natural log of that. And I'm going to plot that versus time. Okay. So how do I get my time lag? My value for that. So this is going to be ln of a at time t minus a at time t plus delta. Right? So what would that be? So if t is 100 seconds, what is 100 plus delta? 175. So where is 175 seconds? It's down here, right? So this is going to be equal to ln of absorbance at time t is this one, right? That's absorbance at 100 seconds minus absorbance at 175 seconds is this one, right? At 175 seconds. So that is my natural log of a at time t minus a at time t plus delta. All right, how about this one? Can I just copy that formula down? This is now going to be ln at time t, which is going to be B23 over here. That's at 105 seconds, minus the absorbance at 180 seconds. So 180 seconds is down here. All right, so that is my ln at B30. This is equal to ln of a at time 105 minus a at time 180, right? So could I have just copied that? 22. So let me see. It should be 23 to 38. So let me copy that one. So it's the same thing. So let me just copy that down to the rest of my column. Right? And how far should I go? How far can I go? So the last data point I can have would be the one that has a corresponding data at 75 seconds later. So 365 minus 375, minus 75 is how much? 290. So I can't go beyond past 290. So I can only go up to 290. Okay. So that's one disadvantage of the method of Guggenheim. You can, but the nice thing about the method of Guggenheim, if there's like an offset in your data, like if there's a systematic error, so your actual the absorbance that you actually read is just concentration times a constant plus another constant, a constant offset, then this is a useful thing to have. Okay. So this is ln of a at time t minus a at time t plus delta. So this time what I'm going to do is I'm going to plot that versus time. So what do I do? Insert, oh, it's almost time. Okay, insert, scatter plot. And what's going to be my data here? My x values would be time, going from 100 seconds all the way to 290 seconds. And my ln of a at time t minus a at time t plus delta is my y. Oops, error. Picked the wrong one. Okay, It should be from 290 to 100 seconds. And this is from 290 to 100 seconds. Okay. And this is my graph. And again, it is a straight line. There's a little bit of a curvature. Okay. And format trend line, I'm going to make my marker smaller. Okay. So there's a little bit of a curvature there. Add trend line, display the equation on the chart, and you can see your slope is pretty much the same, negative 0.0073. What did we have earlier? 17. Okay. So that has to do with the fact that what would explain that discrepancy? Well, you're not using as many data points, right? You don't have as many data points, and there's just some variability there. Okay, but it's essentially the same within the uncertainty of your slope. That's pretty much the same slope.